The weighing room is still dark when the foreman arrives. November air seeps through the wooden walls of the mill building, carrying with it the smell of frost and coal smoke from the overnight watch fire. His breath hangs visible in the lamplight as he crosses the plank floor toward the center of the room, where the platform scale stands waiting. It's a massive instrument. Cast iron frame, brass beam, a wooden platform 12 feet square built to hold raw material crates weighing half a ton. The counterweights hang motionless in the pre-dawn stillness. He's performed this ritual every morning for 2 years. Unlock the building, light the lamps, test the scale with a known weight before the day crew arrives. Trust begins with measurement. Production depends on it. He places a marked iron ingot on the platform. 50 pounds exactly, certified by the state inspector in August. The beam settles. He adjusts the rider weight along the graduated bar, watching the pointer approach equilibrium. It takes 3 attempts to balance. When the beam finally steadies, he leans close to read the graduation, 53 pounds. He lifts the ingot, examines it in the lamplight, sets it down again. The same result. He tests with a second weight, 100 pounds certified. The scale reads 105. He tries the small weights, the ones used for fine materials. Every reading is high, not wildly, not enough to suggest catastrophic failure, just consistently, measurably wrong. But last night, during the final shift, the same weights had balanced perfectly. He'd watched the night foreman test them himself before locking up. The logbook confirms it, all standard weights verified, scale zeroed, no discrepancies noted. The building had been locked from 6 in the evening until he arrived at 5 this morning. No one entered. Nothing changed. Yet somehow, in the 11 hours between, the scale has decided that 50 pounds now weighs 53. He places his palm on the wooden platform. Cold, colder than the air. The metal frame is even colder, the brass beam frigid to the touch. He checks the counterweights. They hang true, no visible shift in the suspension. The knife edges that form the scale's pivot points show no damage, no debris. Everything appears exactly as it should, except the measurements. The morning crew arrives as grey light filters through the high windows. They need this scale. Material calculations for the entire day depend on accurate weight. Iron stock, coal shipments, finished castings, all of it passes over this platform. He makes a decision. They'll recalibrate. They'll test again at midday. If the problem persists, they'll call for an inspector. But by 9 o'clock, something strange happens. The test weights begin reading correctly. By 11, the scale balances perfectly. At the end of the day shift, every measurement matches the certified standards. The foreman tests them again before locking up. 50 pounds reads 50 pounds. 100 reads 100. The logbook entry that night is simple. Morning discrepancy resolved. Cause unknown. Scale functioning normally. The next morning, the same thing happens. The weights read heavy again. The second occurrence would have been easy to dismiss as coincidence, except that it repeated with disturbing consistency. Every morning for a week, the foreman arrived to find the scale reading 3 to 6 pounds heavy on standard test weights. Every afternoon, the discrepancy vanished. Word spread quietly among the mill workers. The men who handled raw materials began double-checking their morning tallies. The bookkeeper who reconciled daily tonnage started noticing small inconsistencies in the overnight inventory records, not enough to suggest theft, but enough to create doubt. Numbers that should have matched across shifts showed subtle variations. Material that had been weighed at shift change, somehow, appeared lighter when the morning crew weighed it again. The mill superintendent called a meeting in the 3rd week. 6 men gathered in the weighing room. The superintendent, both shift foremen, the chief engineer, the bookkeeper, and the man who maintained the scale. They conducted a systematic test. Standard weights ranging from 10 pounds to 500 pounds. Each weight measured 5 times. Results recorded. The morning readings were consistently high, an average of 1.2% above certified values. They repeated the test at noon. The error had dropped to 0.3%. By 4 in the afternoon, the scale read perfectly. They locked the building and posted a night watchman with instructions to check the scale every 2 hours. The watchman's log showed no visitors, no disturbances. At midnight, he tested a 50-pound weight. It read correctly. At 2 in the morning, correctly again. At 4, correctly. When the foreman arrived at 5:30 and tested the same weight, it read 52 pounds. Something was happening in the gap between the watchman's final check and the foreman's arrival. Something occurring in that last hour before dawn. The maintenance man examined every component. He cleaned the knife edges with solvent, checked the levelness of the foundation, inspected the wooden platform for warping. He found nothing wrong. The scale had been installed 3 years earlier, built by a reputable manufacturer in Pittsburgh. It had never required adjustment beyond routine cleaning. Its accuracy had been certified annually. There was no mechanical explanation for intermittent error that corrected itself without intervention. The chief engineer proposed environmental factors. Temperature, perhaps, humidity. The weighing room was unheated. The scale's wooden platform and metal frame were exposed to whatever conditions existed in the building. November had brought cold nights, often dropping below freezing. The days were warmer, sometimes reaching 50 degrees by afternoon. Could temperature affect the scale's accuracy? It seemed unlikely. Balanced scales operated on simple mechanical principles: mass against counterweight, beam and fulcrum, geometric leverage. Temperature might cause metal to expand or contract, but the scale's design accounted for such variations. The knife edges and bearing surfaces were hardened steel, minimal contact area, designed to eliminate friction. The wooden platform was structural, not part of the weighing mechanism itself. Wood might swell or shrink, but that shouldn't alter the balance point. Yet the pattern continued. Morning error, afternoon accuracy, every day. Consistent, measurable, unexplained. The superintendent made his decision. They would continue operations, but morning weights would be verified with a second scale borrowed from the warehouse. Production could not wait for mystery to resolve itself. But the investigation would continue, because something was wrong. And in a facility where precision mattered, where contracts and costs depended on accurate measurement, wrong was unacceptable. By December, the morning discrepancies had become routine, almost expected. The borrowed verification scale sat beside the original, and workers had adopted a new procedure. Weigh everything twice in the morning, record both values, use the lower number. It was inefficient, time-consuming, and it introduced an element of distrust that spread beyond the weighing room. Material suppliers noticed. A vendor delivering iron stock questioned why his certified tonnage didn't match the mill's recorded weight. The mill foreman explained the situation. A scale showing temporary morning errors being investigated, nothing to worry about. The vendor was not reassured. If the mill couldn't measure accurately, how could he trust payment calculations? The conversation ended cordially, but a seed of doubt had been planted. The financial impact was subtle but real. Small overages in morning raw material weights meant the bookkeeper was recording higher material costs than actual. When those materials were processed and weighed again later in the day on the now accurate scale, the finished product weight didn't match the input weight by the expected ratio. It looked like material was being lost in processing. The discrepancies were small, 2 to 4%, but they accumulated across weeks of production. The mill appeared less efficient than it actually was. Insurance inspectors arrived in mid-December for a routine annual audit. They reviewed the weighing logs. They noticed the dual recording system, the crossed-out morning weights, the notes about overnight discrepancy under investigation. Questions followed. How long had this been occurring? What was the cause? Had the scale been professionally inspected? Was the mill certain that material wasn't being removed overnight? The inspectors were polite, but thorough. Trust in measurement was foundational to their actuarial calculations. A mill that couldn't weigh material accurately was a mill with elevated risk. The superintendent authorized a complete professional inspection. A scale technician arrived from Pittsburgh with calibrated test equipment and certification documents. He spent 2 full days examining every aspect of the instrument. He checked the knife edges under magnification, measured the beam geometry with precision tools, tested the platform level, verified the counterweight masses. He tested at different times of day: morning, noon, evening, midnight. His conclusion was definitive. The scale was mechanically sound. There was no defect, no wear, no damage. The instrument was functioning exactly as designed, yet the morning errors persisted. The technician proposed a theory. Perhaps the building itself was settling overnight, creating a slight tilt in the foundation that threw off the scale's level. they tested with a surveyor's transit. The floor was level to within a 16th of an inch across the entire weighing room, unchanged from morning to evening. The building was not settling. Sabotage was suggested quietly, privately. Could someone be tampering with the scale overnight, deliberately introducing error to create confusion? The night watchman was questioned carefully. His log showed no gaps, no unexplained absences. The building remained locked. The scale's components showed no signs of interference. And crucially, tampering couldn't explain why the error corrected itself naturally during the day without any adjustment. A pattern had been observed that no one could explain using conventional reasoning. The scale was accurate in design, sound in construction, properly maintained, correctly installed. Environmental conditions had been considered and found insufficient to explain the magnitude of the error. No external interference was evident. Yet every morning, in the coldest hours before dawn, the scale indicated weight that wasn't there. The foreman began arriving earlier, testing at 4:30 instead of 5:30, trying to catch the transition. They found that the error was fully present by 4 in the morning, sometimes earlier. It existed through the coldest part of the night. As the building warmed, either from winter sunlight through the windows or from the heat of workers and machinery, the error diminished. By the time the building reached 40 degrees, the scale read true. Cold, then. Something about cold. But balanced scales weren't supposed to be temperature sensitive. That was the point of their design. Mechanical advantage, geometric certainty, mass versus counterweight. Physics that didn't change with weather, except something was changing. And it was happening every single night. To understand what was going wrong, the chief engineer first had to document what should be happening. He drafted a detailed explanation for the superintendent, hoping that by articulating the theoretical perfection of the scale's design, the nature of its failure might become apparent. A platform balance scale operates on the principle of the lever, one of humanity's oldest mechanical advantages. A rigid beam, a fulcrum, 2 points of load. In the case of the mill scale, the beam was a heavy brass bar, 6 feet long, suspended at its center point on hardened steel knife edges. The platform where materials were placed connected to one end of this beam. Counterweights hung from the other end. When forces balanced, the beam settled horizontal. When they didn't, the beam tilted. The degree of tilt indicated the degree of imbalance. The knife edges were critical. These were precision-ground surfaces, angled to meet at nearly a perfect line contact, minimizing friction to an absolute minimum. The knife edge supporting the beam at its center rested in a hardened groove, creating a nearly frictionless pivot. This single line of contact was where all the scale's accuracy originated. As long as the pivot remained fixed and the beam remained rigid, the mechanical advantage was exact. 50 pounds on one side required exactly 50 pounds on the other to balance, regardless of temperature, humidity, time of day, or any other external factor. The wooden platform was structural, not mechanical. It distributed load evenly across the 4 steel rods that connected to the beam. Wood was chosen for its stiffness and relatively light weight, important for a platform that had to be large enough to hold material crates, but not so heavy that it compromised the scale's sensitivity. The frame was cast iron for stability and mass, anchored to a stone foundation that extended below the building's floor to eliminate any possibility of settling. Calibration was simple and absolute. Known weights, certified by government inspectors, traceable to national standards, were placed on the platform. Counterweights on the opposite beam were adjusted until balance was achieved. The position of the counterweights indicated the measurement. A sliding rider weight allowed for fine adjustment. Once calibrated, the scale maintained accuracy through purely mechanical means. There were no springs to weaken, no hydraulics to leak, no complex mechanisms to drift out of tolerance. Weight versus counterweight. Geometry. Mathematics made physical. In theory, such a scale could remain accurate indefinitely. Knife edges might wear microscopically over decades, requiring eventual replacement. The beam might corrode if not maintained. But absent physical damage or severe neglect, the fundamental accuracy should persist. Temperature should have minimal effect. Metals expand and contract, but the beam expanded symmetrically, and the knife edges were so small that thermal expansion was negligible. Humidity should have no effect at all on metal and stone. The chief engineer wrote all of this in his report. Included diagrams showing the mechanical principles, calculations demonstrating the geometric relationships, and references to the manufacturer's specifications. He concluded with a statement that felt increasingly hollow as he wrote it. The scale is operating exactly as designed. There is no theoretical basis for the observed errors. Yet the errors persisted. He stood in the weighing room early one morning, watching the foreman place test weights on the platform. 50 pounds, reading 53. He placed his hand on the wooden platform again, as the foreman had done weeks earlier. Cold, very cold. He touched the metal frame. Colder still. He ran his hand along the brass beam, feeling the temperature of the metal where it hung in the frigid air. Everything was cold. He thought about materials, not as abstract principles in engineering textbooks, but as physical substances existing in the real world, responding to real conditions. Metal contracted when cold. He knew this. Wood absorbed moisture from air. He knew this too. But he had dismissed these facts as irrelevant because the scale's design was supposed to be immune to such effects. What if the design wasn't as immune as theory suggested? What if multiple small effects, each insignificant alone, were combining in some unexpected way? He needed to stop thinking about the scale as a perfect machine and start thinking about it as a collection of materials, each responding to the night in its own way. He asked for a thermometer. He wanted to measure temperature precisely throughout the night at multiple locations on the scale. He wanted humidity readings. He wanted to document exactly what environmental conditions existed during the hours when the error appeared and during the hours when it vanished. Because somewhere in that data, the truth was waiting. The chief engineer mounted thermometers at 4 locations: on the wooden platform surface, on the cast iron frame near the base, on the brass beam near the fulcrum, and on the counterweight assembly. He borrowed a hygrometer from the mill's laboratory to measure relative humidity. For 1 week in early January, he recorded measurements every 2 hours from 8 in the evening until 8 in the morning. The data revealed a clear thermal cycle. Evening temperatures in the weighing room hovered around 45 degrees Fahrenheit. Residual heat from the day's operations kept the space relatively warm until about 10 at night. Between 10 and 4 in the morning, temperature dropped steadily, reaching a minimum of 28 degrees just before dawn. The wooden platform cooled fastest, losing heat to the air. The iron frame cooled more slowly, retaining warmth longer due to its mass. The brass beam, suspended in air with minimal contact to other components, cooled to nearly the same temperature as the surrounding air. Humidity showed a related pattern. As temperature dropped, relative humidity increased, even though absolute moisture content remained constant. By 4 in the morning, relative humidity in the weighing room reached 70 to 80%, compared to 40% in the evening. Water vapor was condensing from the cooling air. He correlated these measurements with the scale's error. The pattern was striking. Error magnitude tracked almost perfectly with the coldest temperature and highest humidity. When the room reached its minimum temperature around 4 in the morning, the scale error reached its maximum, typically 5 to 7 pounds on a 50-pound test weight. As temperature rose after sunrise, error decreased proportionally. By the time the room warmed to 40 degrees, error had vanished entirely. The correlation was undeniable, but correlation wasn't explanation. He needed to understand the mechanism. He began with the wooden platform. Wood was hygroscopic. It absorbed moisture from humid air and released it in dry conditions. When the weighing room's humidity climbed overnight, the platform's wood absorbed water vapor. Absorbed moisture caused wood to swell. He calculated the expected dimensional change. A 12-foot square platform, 3 inches thick, made of oak, exposed to a humidity increase from 40 to 75%, would swell approximately 1/16 of an inch in thickness and width. The swelling would be greatest in the direction perpendicular to the grain. But the platform wasn't the weighing mechanism. It was connected to the scale's beam through 4 steel rods. If the platform swelled, it might change the distribution of load slightly, but it shouldn't affect the balance point. Unless, he paused, unless the swelling changed the geometry of how the platform connected to those rods. He examined the connection points. The steel rods passed through holes drilled in the platform's corners. The holes had minimal clearance, just enough to allow free movement without slop. If the wood swelled, the holes would become slightly tighter. The rods might bind. Even slight binding would introduce friction, affecting how freely the platform moved, potentially creating drag that altered the apparent weight. He tested this hypothesis. At 4 in the morning, with maximum humidity and maximum error, he tapped the platform gently while a test weight sat in place. The scale's beam shifted slightly, then settled in a different position. The reading changed by 2 pounds. He repeated the test at noon, when the scale was accurate. Tapping produced no change. The morning binding was real. But binding alone couldn't explain 5 to 7 pounds of error. There had to be more. He turned his attention to the metal components. Brass and iron both contracted when cooled. This was fundamental materials behavior. He calculated the thermal contraction. The 6-foot brass beam, cooling from 45 degrees to 28 degrees, would contract approximately 9/1000ths of an inch in length. Negligible. The knife edges would contract even less. But what mattered wasn't the absolute contraction. What mattered was whether different components contracted at different rates, changing the scale's geometry. The knife edge at the beam center point rested in a hardened steel groove mounted in the iron frame. If the brass beam contracted more than the iron frame, the beam might shift slightly relative to the frame. A shift measured in thousandths of an inch at the pivot point would translate to a measurable shift in the position where the platform loads were applied to the beam. This would alter the lever-arm ratio, the fundamental geometric relationship that defined the scale's accuracy. He did the mathematics. A 9/1000th inch shift in the pivot point, combined with the 6-foot beam length and the 1,000-to-1 mechanical advantage typical of precision scales, could produce an apparent error of several pounds. The numbers aligned with the observed effect. But there was still something missing. The error didn't just appear when cold, it persisted even after the beam had contracted fully. And it didn't vanish instantly when warming began. There was hysteresis, a lag in response. The scale's behavior suggested that some component was slow to return to equilibrium, maintaining a displaced state even after conditions changed. He remembered a lecture from his engineering training. Mechanical hysteresis in flexed members. When materials are stressed, they don't return instantly to their original shape when the stress is removed. Internal friction between grain boundaries, microscopic slipping, residual strain, all these created a memory of the previous state. The effect was small, but in precision mechanisms, small effects mattered. The brass beam was under constant stress, flexed slightly by the weight of the platform and counterweights. As it cooled and contracted, internal stresses redistributed. When it warmed, it didn't immediately return to its original geometry. It relaxed slowly over hours. This lag explained why the error persisted into the early morning even as warming began, and why accuracy returned gradually rather than instantly. He assembled his findings: wood swelling from overnight moisture, creating binding and friction; metal contraction altering pivot geometry; mechanical hysteresis maintaining displaced states longer than thermal conditions alone would suggest. Each effect was small, but they weren't independent. They were cumulative, interactive, mutually reinforcing. Together, they created an error large enough to matter. The scale wasn't broken. It was responding precisely, mechanically, to the conditions it experienced. It was measuring not just weight, but the night itself. The chief engineer presented his findings to the superintendent in a meeting held in the weighing room itself, with the scale as their subject. He brought his data, his calculations, and a proposal for verification experiments. If his hypothesis was correct, they should be able to reproduce the error artificially by controlling temperature and humidity, and they should be able to eliminate it by modifying the scale's susceptibility to environmental conditions. They began with verification. On a mild evening in late January, they closed the weighing room and artificially cooled it using open doors and fans, bringing the temperature down to 28 degrees. They introduced humidity using pans of water placed near the scale, allowing moisture to saturate the air. They waited 4 hours, monitoring conditions, then tested the scale. Error appeared, 5 pounds on a 50-pound weight. They warmed the room using portable stoves, reducing humidity by ventilation. Within 2 hours, the error had diminished by half. Within 4 hours, accuracy had returned. The experiment was repeated with controlled variations. They cooled without adding humidity, the error was smaller. They added humidity without cooling, the error was minimal. They cooled and humidified together, the full error appeared. The interaction between temperature and moisture was essential. Neither alone was sufficient. Together, they created conditions that altered the scale's mechanical response. They examined each component in detail. The wooden platform showed visible moisture accumulation on cold, humid mornings, a thin film of condensation that dried as the room warmed. They measured the platform's dimensions at different times of day using precision calipers. The thickness varied by nearly 1/8 of an inch between the driest afternoon conditions and the dampest pre-dawn conditions. The expansion was enough to create measurable binding at the steel rod connection points. They removed the brass beam from the scale and measured its length at different temperatures using a precision comparator. The thermal contraction matched theoretical predictions, 9/1000ths of an inch over the 17-degree temperature range. They measured the iron frame's contraction under the same conditions. It contracted less, approximately 6/1000ths of an inch. The differential contraction was 3/1000ths of an inch, sufficient to shift the pivot point and alter the lever arm geometry. They tested the beam for mechanical hysteresis by flexing it under load, releasing the load, and measuring how quickly it returned to its original shape. At room temperature, recovery was rapid, within minutes. At 28 degrees, recovery was slower, over an hour. The cold metal's internal friction was greater, slowing the relaxation of residual stress. The maintenance man, watching these experiments, offered an observation from his years of experience with machinery. Components that seemed identical when new often behaved differently after years of service. Wear patterns developed. Internal stresses accumulated. Materials aged. The scale had been in service for 3 years. Perhaps some subtle change had occurred over time, making it more sensitive to environmental conditions than when it was first installed. They examined the knife edges under magnification. The steel showed microscopic wear, not enough to compromise accuracy under normal conditions, but enough to slightly alter the contact geometry. The worn edges might have less tolerance for thermal shift, might be more affected by the differential contraction between brass and iron. A new scale might not show the same error. This particular scale, with its particular history, had developed this particular sensitivity. The superintendent asked the essential question. Could they fix it? Could they modify the scale to eliminate the environmental sensitivity while maintaining accuracy? The chief engineer proposed 3 modifications. First, construct an insulated enclosure around the entire scale, maintaining a more stable temperature and humidity environment. Second, replace the wooden platform with metal, eliminating the moisture absorption problem entirely. Third, install the scale on a heated foundation, preventing the base temperature from dropping below 40 degrees, even on the coldest nights. The costs were calculated. The downtime was estimated. The superintendent approved, but he also made a different decision. The current scale would remain in service, unmodified, but with its behavior now understood and documented. Morning weights would continue to be recorded with the understanding that they required a correction factor based on room temperature. The verification scale would remain in place for cross-checking. Why not fix it? Because the scale was teaching them something valuable. It was demonstrating that precision measurement was never absolute, never independent of environment. Every instrument had environmental sensitivities, even when designed to minimize them. Understanding those sensitivities, documenting them, accounting for them, that was more valuable than pretending they didn't exist. The scale would stay, the measurements would continue, but now they understood what they were measuring. The complete explanation required acknowledging that mechanical systems are not abstract ideals, but physical assemblies of real materials, each with properties that respond to their environment. The scale that grew heavier overnight was not malfunctioning. It was demonstrating the limitations of any measurement system when environmental factors interact with material properties. Three mechanisms combined to create the observed error. The first was moisture absorption in the wooden platform. Wood is hygroscopic. Its cellular structure contains microscopic voids that absorb water vapor when relative humidity is high and release it when humidity is low. During cold overnight hours, as room temperature dropped and relative humidity increased, the platform's oak timbers absorbed moisture from the air. This absorption caused the wood to swell, expanding perpendicular to the grain direction. The platform increased in thickness by up to 1/8 of an inch over the course of a humid night. This swelling tightened the clearance around the steel connection rods that joined the platform to the scales beam. The rods, which should have moved freely within their mounting holes, began to bind against the swollen wood. This binding introduced friction into the system. When a weight was placed on the platform, the friction resisted the platform's movement, requiring slightly more force to overcome. The scale interpreted this additional force as additional weight. The effect was cumulative. The more binding, the more apparent weight. As the building warmed during the morning and the wood dried, it contracted, clearances opened, friction decreased, and the error vanished. The second mechanism was differential thermal contraction between the brass beam and the iron frame. All metals contract when cooled, but different metals contract at different rates. Brass has a higher coefficient of thermal expansion than iron. Over the 17-degree temperature drop experienced overnight, the 6-foot brass beam contracted approximately 9/1000ths of an inch in length, while the iron frame contracted only 6/1000ths. This 3/1000th inch differential meant that the beam contracted more than the structure supporting it. The critical consequence occurred at the pivot point. The knife edge supporting the beam at its center rested in a groove in the iron frame. As the brass beam contracted more than the iron frame, the beam center point shifted slightly relative to the frame. This shift altered the lever-arm ratio, the geometric relationship between the platform connection point and the fulcrum. A shift of 3/1000ths of an inch at the fulcrum over a 6-foot beam length translated to a measurable change in apparent weight. The scale's mechanical advantage, normally exact, became slightly asymmetric. Weights on the platform side required slightly more counterweight to balance. The third mechanism was mechanical hysteresis in the beam itself. When materials are flexed under load, they store elastic energy. Ideally, when the load is removed, the material returns instantly to its original shape, releasing all stored energy. In reality, internal friction prevents immediate recovery. The material relaxes slowly, over time, as internal grain boundaries slip and residual stresses redistribute. This delayed recovery is mechanical hysteresis. The brass beam supported constant stress from the platform and counterweights. As it cooled overnight, internal stresses redistributed due to thermal contraction. The beam assumed a slightly different equilibrium geometry at cold temperature. When warming began in the morning, the beam didn't instantly return to its warm temperature geometry. It relaxed gradually over several hours. During this relaxation period, the beam retained a memory of its cold temperature state, maintaining a slight geometric distortion even as temperature increased. This hysteresis extended the duration of the error beyond what thermal conditions alone would predict. These three effects, moisture-induced friction, thermal contraction altering geometry, and mechanical hysteresis delaying recovery, were each insufficient alone to create the observed error. But they didn't operate independently. They occurred simultaneously during the same overnight cold period, and their effects compounded. Wood swelling added friction. Thermal contraction shifted the pivot. Hysteresis sustained both effects longer than expected. Together, they created a 5 to 7 pound error on a 50-pound weight, an 11 to 14% discrepancy. The scale wasn't measuring just mass anymore. It was measuring temperature through thermal contraction. It was measuring humidity through wood swelling. It was measuring time through hysteresis. The instrument had become a complex environmental sensor responding to the night's conditions with mechanical precision. This explanation satisfied the engineers because it was testable, quantifiable, and consistent with known material science. But it raised a deeper question. If this scale, designed for precision and carefully maintained, could develop such environmental sensitivity, what about other instruments? How many measurements, in how many industries, were being affected by unrecognized environmental interactions? How much trust in measurement was based on assumption rather than verification? The mill's solution was pragmatic. Morning weights would be corrected using a temperature-based factor derived from experimental data. The verification scale would remain in service. Routine checks would continue, but the fundamental lesson endured. Precision is conditional. Accuracy depends on understanding not just the instrument, but the environment in which it operates. The scale remained in service for another 12 years. It was eventually replaced, not because of its environmental sensitivity, but because the mill's production capacity expanded beyond what the platform could accommodate. The brass beam was saved, donated to a technical institute where it was used for decades as a teaching tool in a course on materials behavior and measurement error. On cold mornings, when students measured its length at different temperatures and observed the thermal contraction, they were told the story of the scale that grew heavier overnight. Not as a cautionary tale about faulty equipment, but as a reminder that the physical world is more complex than theory suggests, and that the best measurements are made by those who understand not just their instruments, but the invisible forces acting upon them. The scale didn't grow heavier overnight. The night changed it. Wood absorbed moisture, metal contracted, geometry shifted, and in that transformation, precision became conditional, accuracy became contextual, and measurement became a negotiation between instrument and environment. The scale was working perfectly. It was doing exactly what materials do when temperature drops and humidity rises. It was responding to the night, mechanically, inevitably, with absolute physical honesty. The error wasn't in the scale. The error was in expecting that steel and brass and wood could remain unchanged by the world around them.